Okay, good evening, everybody. Okay, and welcome to another session of organic chemistry. In today's session, we are going to continue our discussion of Chapter 3. But before we do that, I do have a few announcements to make. The first class exam is scheduled for a week from Thursday, and that will be Thursday, September 26th. Okay, because of that exam, I have posted the fall 2012 first exam in Blackboard. So I advise that you want to take a look at this exam so you know exactly what this the coming exam will look like. Also, on Monday, this coming Monday, we are going to have an online review session, and for that session, we are going to use the fall 2012 first exam for the review session, the online review session. That will be Monday, 8 o'clock. This coming Monday, 8 p.m. So what I will do, I will send you an email with the link of how you come to the virtual classroom. Okay, and then I will also show you how to use the virtual classroom once you get inside the class on Monday. So that will be, so mark your calendar, that will be 8 p.m. next Monday. Also, I do have your quiz graded. The last quiz has been graded. I will give this back to you at the end of class today. Yes, you have a question?
Yeah, for the online test you're going to be posting, will you be posting solutions for it as well so we can check our answers?
No. Go to the section. If you go to some of the sessions that I had last year, all of those are posted in YouTube. I could post them in Blackboard also.
Okay.
You know, in other words, the session that we had last year in terms of the review session, yeah, those I will post those in Blackboard, so you get a chance to look at them. Okay, so now let's get started with today's discussion. Okay, as promised, we are going to discuss the chemistry of alkanes, which we started last Thursday. Specifically, we will discuss the nomenclature of alkanes, discuss the different classes of organic compounds, constitutional isomers, conformational isomers, and finally we will start a discussion of reactions of organic compounds. Okay, this slide, of course, is a list of learning outcome objectives. This list of learning outcome objectives you should use as a study guide for the content of this chapter. Okay, before we left on Thursday, we were discussing some of the physical properties of alkanes. Of course, we know that alkanes are those compounds that contain carbon and hydrogen atoms in which all of the bonds are sigma bonds or single bonds. We also refer to alkanes as hydrocarbons because they contain carbon and hydrogen atoms. In this case, we refer to them as saturated hydrocarbons. because they do not have multiple bonds, or they have a single bonds. Okay, so when we left, we told you that the low molecular weight alkanes, in this case methane, ethane, propane, and butane, they are all gases because they have very weak intermolecular attractive forces. We also gave you the list of intermolecular attractive forces. Told you we have the van der Waals forces, we also told you we have the dipole-dipole interaction. And also we told you we have the hydrogen bonding. These are all what we call the intermolecular interaction, or intermolecular attractive forces. Now, before we left, we told you that the alkanes only have the van der Waals forces, which are very weak compared to the dipole-dipole and the hydrogen bonding. So they do not have hydrogen bonding, and they do not have the dipole-dipole interaction. So we simply just, let's take this out. For the van der Waals forces, if you take a look at the alkane molecule, take a look at this molecule here, we know that the alkanes are non-polar molecules. They are non-polar molecules. In other words, if you take a look at, think of the alkanes as just a ball of electrons, so you have even distribution of electrons within the molecule, and I saw there is no dipole moment. And because of this, think of the alkanes, like I said, as just ball of electrons like this, in which electrons are moving around the molecules. And as such, there will be some time, think of a possibility in which one part of the molecule could have what we call a temporary negative, partial negative charge, and another part will have a temporary partial positive charge. And any alignment of these temporary charges, for example, on another molecule here, this would be temporary negative charge here, temporary positive charge. This attraction here is what we refer to as the van der Waals attraction. Which is essentially a result of temporary dipole, resulting from temporary dipole. And the van der Waals forces are very, very weak. And that is why, for the most part, the alkane molecules, those that are low molecular weight, are gases, because they do not have enough attraction between the molecules. Now, when we now begin to increase the molecular weight of the alkanes, the bigger the molecule, the bigger the van der Waals attraction is. If, for example, we take a look at, this is butane right here, say we take a look at pentane, which has 5 carbon atoms. Whereas the butane has a boiling point of -1 degrees. Now, because of the bigger size of pentane molecule, the boiling point is 36 degrees, yes.
The carbon.
Oh, I'm sorry. Thank you. Thank you. Okay. The pentane. Okay. A bigger molecule than butane. Therefore, the van der Waals interaction is now bigger. So now it is, the boiling point is now 36 degrees. So actually, this is a liquid. This has now become a liquid. Now, if you go to another, the next bigger molecule, alkane molecule, which will be hexane. For the hexane molecule this here, the boiling point is 68 degrees. So therefore, the bigger the alkane molecule is, the bigger the van der Waals interaction. Indeed, when it gets to very, very large alkane molecule, that those that make up your Vaseline, petroleum jelly, those are a lot of those contain a lot of alkanes. At that point, they're becoming solid because the molecules are so big. Okay? So anyway, so the van der Waals interaction is very important with regard to the alkane molecules. Now, another information I want to give you before we go to nomenclature of alkane, if you take a look at each one of the alkane molecules, the carbon atom in the alkane molecule, of course, it's an sp3 carbon atom, and this stereochemistry is a tetrahedral geometry. If you look at this would be a tetrahedral geometry. See? Where the carbon is sitting right in the middle of a tetrahedron. Around the carbon atom. Also, if you take a look at the molecular formula for each one of the alkanes, they all have a general formula of Cn H2n plus 2, where n is the number of carbon atoms in the molecule. N equals to number of carbon atoms in the molecule. N equals to number of carbon atoms in the molecule. For example, if you look at this here, the formula is C2H6 for ethane. For propane is C3H8. For butane is C3, C4, H10, so and so on and so forth. So the general formula does hold for all alkane molecules. So therefore, supposing I give you this question. Supposing I give you this question. I give you all of these molecules here, 3 molecules. A, okay, C, 6, H, 10, B, say C, 8, H, 18, and C, 7, H, 14. And I ask you, of these 3 molecules, A, B, C, which one is an alkane? Exactly. So that is what you use the formula for. B is the alkane in this. Of all the 3 here, B is the alkane. So you could use the formula to determine whether, if I give you a formula, you could say, oh, this is an alkane. Okay? So at this point, let us begin to look at the nomenclature of alkanes. Nomenclature of alkanes. If I give you this molecule here, if I give you that molecule, we refer to this as a straight chain alkane. Straight chain alkane. We say this is straight chain alkane because if you look at all of the carbon atoms, they are attached to each other in series. Carbon attached to this carbon, to this, to this, to this. They are attached to each other in series. So we call this a straight chain alkane. And therefore, if you look at this table here, we have given you the names of all the straight chain alkane from carbon 1, in this case, to carbon 20. You need to know those names because those will serve as the basis for the nomenclature of most organic compounds. You need to commit those names to memory. Okay, let us go through them. Okay, of course, the first one with only 1 carbon atom, we call that methane. Whenever you have 2 carbon atoms, see, ethane, 3 propane, 4 butane, 5 pentane, 6 hexane, 7 heptane, 8 octane, 9 nonane, 10 decane, and continue like that. Of course, 11 undecane, 12 dodecane. In other words, you have 2 more carbons above 10. 13 tridecane. Finally, you get to the 20, which is isocane. Now, supposing you have 14, C14. C14, we call that, what are we going to call C14? Tetradecane, exactly. Tetra. Decane. C15 becomes penta. Decane. In other words, 5 carbons above decane. C16 becomes hexadecane. C17 becomes heptadecane. C18 becomes octadecane. C19 becomes nonadecane. Now, all of these names are what we call the IUPAC names, or systematic names. And IUPAC stands for International Union of Pure and Applied Chemists. And the acronym is IUPAC. So you are going to hear me say IUPAC all the time. And this is the acronym for that. Okay? So in other words, systematic names. Some of the alkanes may have common names. When we get to that, I will let you know that this is a common name. But for the most part, what I want, if I ask you for the name, I will be asking you for the IUPAC name or the systematic name. Okay?
Does the C mean chemist? Or does
Chemist, yes. Okay, so these names, you need to know them. There is no getting around it. You really need to know them. You have to commit those names to memory, because they will serve as the basis for the nomenclature of most organic compounds. Okay? Now, before we get more into the nomenclature, there's another thing I want to show you. What we call alkyl groups. What we call alkyl groups. America, what are alkyl groups? Very good, and thank you. In other words, alkyl groups are molecules in which you have taken out one hydrogen from an alkane molecule. For example, if I have this, supposing I take out this hydrogen here for methane. If I take out this hydrogen here, then I get this, which is what you have here. So I get this. So I call this an alkyl group. And to give this name, to come up to derive the name of the alkyl group, what you do, you replace the last A and E of the corresponding alkane name, you replace with YL. In other words, this becomes a methyl group.
Do you want to show the broken bond?
Yeah, you have to let you know that there is nothing attached to here for now. It's a fragment.
Not the actual picture, not your picture, but that. You want to draw that?
This here?
Yeah.
No, you don't need to. Well, just put this line here. Just put that line. This is nothing but a fragment. Okay, I will consider this an alkane fragment. Okay, now supposing I have this. Supposing I have this. and I take up one hydrogen from ethane. This is ethane. I remove one hydrogen from it. What do I get? I get this fragment here. And what am I going to call that fragment? Or alkyl group? What are we going to call that? That becomes ethyl, exactly. So that becomes ethyl. So that is an ethyl group. Supposing I have this, and I have this here. So what do I call that alkyl group? Keep in mind this is butane. And you remove the last ANE and replace this YL. So this becomes butyl. Okay, butyl group. Very good. Okay. Okay, so having given you that information, let us now begin to take a look at nomenclature of alkanes. For that, I have given you here a set of rules that will allow you to use the IUPAC nomenclature. In other words, this is a guide that is essentially provided by the IUPAC group for the nomenclature or the systematic naming of alkanes. If, for example, I have this, we already know this is hexane, right? We know that is hexane. Now supposing I now come here, take this out, take this out, and now place a methyl group here. At this point, this is no longer a straight chain alkane. This is now what we call a branch alkane. A branch alkane. And to name this, what we do, follow rule number 1. We look for the longest carbon chain, the longest continuous carbon chain in this molecule. In this case, the longest continuous carbon chain, if you want to do that, would be 1, 2, 3, 4, 5, and 6. That would be the longest carbon chain. And then we assign a number. Now this here, this methyl group that is here, we now consider that methyl group as a branch or substituent. As a branch or substituent. Okay. So now to name this molecule here, we give the position of the branch or the substituent. We separate the name from the number with an hyphen, so we say 2 hyphen methyl, because there is a methyl group in the 2 position, and then we give the name of the straight chain alkane. That becomes what we call the base name. So now becomes 2-methyl-hexane. 2-methyl-hexane. Okay, supposing I have this. Notice what I'm doing here, removing one hydrogen, and I want to replace with an alkyl group. Supposing I have this here. Okay. Now, what is the longest carbon chain here? Going from here, we say I have 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. Doesn't really matter at this point, right? Now, if you want to name this, you go back to numbering. 1, 2, 3, 4, 5, 6. According to the IUPAC guidelines, you have to number the carbon, the longest carbon chain, so that the branches or the substituent will have the lowest combination of numbers. The branch or substituent will have the lowest combination of numbers. That would be rule number 3. That would be rule number 3. So how do we name this one here? Okay, the question is, where do we start counting, assigning the numbers? Do we start from right here, or do we start from right here? If we start from here, these branches will be in 2 and 4, right? So 2 plus 4 is 6. But if we start from here, this will be 1. The branches will be in position 3 and 5. 3 plus 5 is 8. So where do you want to start? You have to start from the left in order to give the lowest possible combination of numbers to those substituents. You follow that? Okay, so in this case, so this becomes, the branches are in 2 and 4, another set of rules, which is also part of the rules 1, 3, and 4. When you now name the substituent, you have to name the substituent in alphabetical order. Okay? So this becomes 4-ethyl, because the E comes before the M, methyl, and the ethyl is in the 4th position. So another hyphen. Keep in mind, you separate the number from the word using an hyphen. Then you say 2-methyl. Then finally, you then include the base name. Then you include the base name. The base name here is what? What is the base name? Hexane, exactly. Okay, so the longest carbon chain, the longest continuous carbon chain will be used as the base name, or sometimes we refer to as the parent name. And then once you determine that, then you assign the numbers based on those other rows. Yes, Kara.
So for the 4-ethyl, if there was another carbon chain there, you would have to go down. You have to go to 4 and then go down. Keep counting.
If there is another, yeah, we're going to get some of that. In other words, the longest carbon chain is what we're looking for. Yeah, by the time we finish this chapter, we'll get to that exactly. Very good. Okay? So anyway, the rules that I've just used now, these are rules 1, 3, and 4. Okay? Now let us take a look at rules 2 and 5. Rule 2 says, if there are more than one longest carbon chain in the molecule, use the one with the more or most branches. Okay. Okay, so let us go to a new page for that. For rule 2. Okay, supposing I have this molecule here. Okay, so how many carbon do I have here? That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Okay, so what would be the name of that alkane? What is it? Undecane. Very good. So that would be undecane. Very good. That would be undecane. And that would be a straight chain alkane. Now supposing I have this. Take this hydrogen out, replace with an alkyl group. Take this one out. Place this with a metal. Okay. So how do we name this molecule? The first thing you have to do, of course, is to determine the longest carbon chain. Okay, so what is the longest carbon chain in this molecule? Keep in mind, you could count from here, 1, 2, you could go from here to here. Keep in mind, the longest doesn't mean the way the molecule looks. It simply means you are able to go from one carbon to the end of the chain without retracing yourself. So you could go from here, to here, okay? You could go from here to here, depending on whatever the longest carbon chain is, or you could go from here, to here. Okay, so which is the longest carbon chain?
There's 2 longest carbon chains.
Which one?
The one straight one.
What's the base name? What would be the name? Undecane. So going from here to here? Okay, that's the longest carbon chain? Okay, that is correct. That's 11. Okay, about here, let us see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. About that one. What is wrong with that?
One of them has more substitutes.
Exactly. Okay, according to rule number 2, whenever you have a choice of the same numbering, in other words, you go either way and you get the same type of base name, then to make your decision has to be the one that has the most number of branches will be the base name. In this case, if we use this here, if we use this as the base name, how many branches does it have? 1. Okay, it has 1. On the other hand, if we use this as the base name, this one here, how many branches does it have? 2. Because this metal is a branch, and this butyl is a branch. So in that case, you have to use the one with the longest number of substituents. You follow that? Okay, that is rule number 2. Okay, so if we do that, So what will be the name of this? Let me take this out. Okay, now the next question is, where do you start to number? Where do you start to number? Okay, let me call this here. Let me call this side A. Let's call this side B. Where do you start the number from? From A? Why? Give you the lowest combination of numbers for the substituent. Okay? And that is rule 3. Okay? So very good. So therefore, we are going to start numbering from here. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now, do not forget, what I keep telling, do not be fooled by the way the molecule is written. Okay? Okay, so this is the base name, and therefore, what is the name of this molecule? Okay, you guys need to give me the name. Yes. Arona? Oh, yeah, what do you see? 5, okay. Butyl, why butyl? It comes before methyl, right? Okay. So it's a 5 butyl because of this group right here, right? Okay. 3, very good. 3 methyl and undecane. Very good, excellent. So you guys are now experts on nomenclature of alkane. I don't need to talk anymore about nomenclature. Right? Okay, now. Okay, so that is 5 butyl, 3 methyl undecane. That is rule number 2 that we just did. Now, let us go to rule number 5. Rule number 5. Okay, everybody follow this so far? Nomenclature is very easy. I tell you now, this is where most students do well. Most students do very well with nomenclature. And they do not do too well with resonance. I don't know why, but somehow resonance seems to give students a lot of trouble. By the way, those of you who continue to have problems with resonance, come and see me in my office, okay? So that I have one-on-one with you to explain exactly what is happening. Okay, now. Okay, you got this? Okay, now I want to go to rule number 5. With rule number 5, okay, let me take this out. Rule number 5 simply says, whenever you have a complex substituent, you got to treat the substituent as an alkane molecule by itself. Okay, supposing we have this. Supposing we have that. What would be the base name or the parent name for this? Base name. Or sometimes we call it parent name. Okay, what is it? Dodecane. Okay, very good. So you want to start numbering from where? Let's say this is the left and this is the right. Where do you want to start numbering? In other words, if you're going to name this as dodecane, you are telling me this is your branch, right? Okay, very good. So where do you want to start numbering, left or right? This is left and this is right. From the left? Okay, and why? Because it gives you the lower number. Excellent, excellent. I think you guys are becoming master of nomenclature. Okay, so we have to start numbering from here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, so now this is the substituent. Now we have what we call a complex substituent. or a complex branch. So in this case, what do you do here? Okay, you treat the substituent as if you are treating, you know, an alkane molecule, or an alkyl molecule. If you take a look at this, take a look at this. Look at this part of the molecule here. Look at this part of the molecule here. What will you call that? What will you call that? As an alkyl group. A butyl group, right? Okay, very good. So that's a butyl group. Okay, now if you look at where the butyl group is attached to the parent chain, right here, on this carbon here, that butyl group is attached to the parent chain on this carbon, and therefore you regard this carbon as carbon number 1 of the butyl group. So this becomes carbon number 1 of the butyl group. That is 1, 2, 3, and 4. Okay, now just consider the alkyl group as a name by itself. So you name it, and then you ask yourself, now the alkyl group also has a branch. So now this is the branch of the alkyl group. And what do we call that branch? A methyl. And what position of the butyl is the methyl? 2. So this becomes 2 methyl butyl. So that is what the name of this is right here. So that is 2 methyl butyl. Okay, so you name the complex alkyl group by itself. Now you're now going to attach it to the base name or the parent name. So how do we? What will be the complete name? What position is it? It's in the 6th position. So you now say 6. You now say in this case 6 hyphen, then use parent 2 methyl butyl. In other words, this complex group is in the 6th position of dodecane, because dodecane is the parent name or the base name. You follow that? Okay, that is rule number 5. So at this point, we are going to be doing the nomenclature all through this discussion of this chapter. So I am going to stop the official treatment of nomenclature at this point and go to another concept. Okay, unless you have a question. Yes.
So how the methyl group is on the 2 for the butyl, if that methyl group happens to be on the 3, would it?
Yes.
You wouldn't try to make it the lowest number, right?
Oh no, you just whatever it is. Yeah. Because you have to consider this carbon here. Very good question. You have to consider this where the attachment is as number 1, regardless of what. Okay, in that case, if the methyl was here, it would be 3 methyl. Okay, very good. Okay, so now let us go to another concept that you guys will like. Not that. Okay. How much time do we have? Oh, we got plenty of time. Okay, very good. Now, let me see, who do I call on here? I'm trying to know you guys' names. I call on those people that I know. Okay, Shanti, I think I know your name by now. Yeah, can you tell us, the next concept we want to discuss is what we call constitutional isomers. Do you know what constitutional isomers are? Okay, thank you. So constitutional isomers are different compounds with the same molecular formula, but different attachments of the atoms. Now that we know how to name alkanes, we now want to begin to look at the different ways in which carbon atoms will attach itself to begin to give us what we call constitutional isomers. Take a look at these two molecules here. This is butane, right? Molecular formula for this will be C4H10. This molecule here, what is the IUPAC name for this? 2-methyl what? Propane, okay, which is what this is right here. So the IUPAC name is 2-methyl propane, because in this case, the parent name is this here. And methyl group is in 2 positions, okay? But the 2-methyl propane, by the way, this name isobutane, that is a common name. This is a common name right here. Okay? The butane and the 2-methyl propane, they have the same molecular formula. So therefore, these two molecules, therefore, even though they are different compounds, we call them constitutional isomers. What is the difference between them? The attachment of the atoms are different. Whereas in butane, you have a straight chain molecule. In 2-methyl propane, you have a branch alkane molecule. Okay? Because they are different compounds with the same molecular formula, we call them constitutional isomers. Okay, so having said that, let us see now. Supposing now I give you this formula here. C5H12. Is that an alkane molecule? Is that an alkane molecule? Yes. Can you give me all of the constitutional isomers of this molecule? Okay, let's start. Okay, the first one, straight chain, right? The first one, straight chain alkane. Okay. And the name for this will be pentane. Okay. So now in this case, all of the carbon atoms are attached linearly, right? In series. Okay, any other possibility? Let me simply label this. Let's say carbon 1, 2, 3, 4, 5. Okay, any other possibilities? You use the number to tell me where to put the carbon.
You can say one off to get destroyed by.
Okay. Okay, take out one. Very good. Take out one and put it on 3. Okay, very good. So I will take this out and place it right here. That's a different attachment. Okay. So therefore we have this here. And now, what will be the name of this? 2-methyl butane. Okay. This and this, the pentane and the 2-methyl butane are constitutional isomers. Because they have different attachment of the atoms, even though they have the same molecular formula, which is C5H12. Okay, any other possibilities? Starting from pentane. Yes. Dimethyl propane. Very good. So you want me to do this? So propane being the base name. And that is the beauty of carbon molecule, because carbon has the capacity to bond to itself. You could almost form almost unlimited number of organic molecules if you have enough carbon atom in that molecule. Okay, so now this is also a constitutional isomer of these two here. So what would be the name here? You say two. Okay, what would be the real name? 2. It has to be 2,2, because you have, yeah, you got to indicate the, since you have methyl on those 2 carbons, 2 of them, so you have to say 2,2, 2 comma. Anytime you have the number, you separate the number with a comma. 2,2 dimethyl. Now, whenever you have more than one branch of the same, then you use the prefix di. If you have 2, if you have 3, you say tri. If you have 4, you say tetra. Okay. So in this case, become di-methyl propane, because propane is the base name. This is your base name right here, propane, and the methyl is in the 2 position. Yes.
I know the first 2 is the carbon is on, but the second 2, how come we have to put that? You just said dimethyl. That means you have 2 methyl groups on 2, on position 2.
No, you cannot say that. You have to indicate that both of the, for each substituent, you got to put a number on it.
No, I'm saying, aren't you basically repeating yourself by saying 2 dimethyl? I know the first 2 is for the position of the carbon, but the second 2 means you have 2 methyl groups on the second carbon, right?
Oh, no.
What does the second 2 mean?
2,2 means that you have 2 methyl groups on the 2 position. That's what it means.
So what's the dimethyl? Dimethyl means you have 2 methyl groups.
I know, but that is the convention. You have to indicate those positions. Yeah, I know what you're saying, because it's only 3 carbon atoms. Supposing you have this, okay? The reason you say, I know why you say that, because you only have 3 carbon atoms. Supposing you say you have this. But it's a good question, though. What will you call that? Okay, 2,2 dimethyl pentane, exactly. Because if you just say dimethyl, you don't know where those methyl is. So here you got to say 2,2 dimethyl pentane, because if you just say dimethyl, they could be on 2, they could be on 3, so you cannot just say that, okay?
Right, I guess my question is, how come not put the di?
Okay, now let's continue this discussion in my office, okay? Yes. To do what? For each substituent you have on a carbon atom, you got to put a number on it.
But the machine thing, why can't you just say 2 dimethyl? Right, because dimethyl.
No, but you cannot do that. Okay. That is not the convention. That is not the guideline. Okay, the guideline is you must put a number on every branch. Okay. Okay, so let's move on that. Anyway, the question I ask for you is, give me all of the constitutional isomers. Okay, so what other constitutional isomer do you have here? Is there any other? Or is it? 3-methyl butane, let us see. It's a 3-methyl butane. Okay, let us look. I don't think that will work, but let us see here. Okay, so that's butane. So where is 3? But don't forget you have to assign the lowest possible number. Okay, so you say that I should take this out, right? And say this is here. You say 3, right? From where you start counting. But you got to give the number so as to give the lowest possible number to the branch. Huh? So you have to start counting from here. 1, 2. That is what we have here. 3 and 4. So we have 2-methyl. We have 2-methyl butane, which is the same as what we have here. I know, but you cannot have 3-methyl, because if you say 3-methyl, you are start counting from here. You cannot do that. You got to start counting so that you give the lowest possible number. You got to give the branch the lowest possible number. Okay? When you start counting, you got to count from the side that will give the branch the lowest possible number. So anyway, in this case, we only have 3 constitutional isomers. Yes. Yes. To do what? 2-ethyl propane. Okay, let us see. Maybe that might work. 2-ethyl propane. Let us see here. So we have propane. And you say 2-ethyl, right? So I take this out. I put an ethyl group here, right? Okay, very good. Let's see whether that works. Okay, supposing I tell you to give the name of that compound, what will it be? Exactly. So if you start counting from here, 1, 2, 3, and 4. So you see, end up with 2-methyl butane. It isn't the way you write the molecule, okay? Because sometimes that could be misleading. So which is this and these are the same. Okay? So in this case, we only have 3 constitutional isomers coming from this formula. Huh? Okay. Okay. So now let us go to another concept I want to share with you today. Let us now begin to take a look at the different types of carbon atoms in an organic molecule. Now that we know how to name at least the alkanes, take a look at the different types of carbon atoms in organic molecules. We essentially have 4 different types of carbon atoms. This is very important. So at this point, we now want to begin to talk like organic chemists. Okay? So we are going to be giving you some of the terminology, the nomenclature that you need to use to talk like organic chemists. We have what we call a primary carbon. For the primary carbon, in this case, say I have this here. This carbon here. This carbon here is a primary carbon because it is only attached to one other carbon atom. Okay? So this is a primary carbon. And we generally represent it as this here, primary carbon, because it is only attached to one other carbon atom. And this carbon here, we call this a secondary carbon. Because it is only attached to how many carbons? 2 carbon atoms. Okay? This attached to this carbon here and this carbon here. Okay? And we sometimes we represent as this here. Now we could also have, say we have this here. This carbon here, we call this a tertiary carbon. Because it is attached to how many carbons? 3 carbon atoms. Okay? And sometimes we represent as this here. And that is this case here. This is the tertiary, this is the secondary, and this is the primary. And finally, we could also have what we call a quaternary carbon. This carbon here is your quaternary carbon. That's your quaternary carbon because it is attached to 4 different carbon atoms. So those are the 4 different types of carbon you have in organic molecules. Now, since you have those different types of carbon, the hydrogen that are attached to them are similarly described. For example, the hydrogen that are attached to the primary carbon, what do we call them? We call them primary hydrogens. These hydrogens here, we call them primary hydrogens. The hydrogen that are attached to the secondary carbon, what do we call them? Secondary hydrogens. And the hydrogen that is attached to the tertiary carbon, because there has to be only one, we call it a tertiary hydrogen. The hydrogen attached to the tertiary carbon, we call it a tertiary hydrogen. This is very important going forward because you will simply hear me say, this is tertiary carbon, primary carbon. You need to know exactly what I am referring to. Okay, now, before we leave, I think I still have about 10 more minutes to go. Oh, see, I have plenty. I think of plenty of time. Now let us shift gear.
Oh, you have to get out the quizzes, so
yes, I got plenty of time to do that. I know you. Okay. Just let me know when it's 5 minutes to the end of class. I know you let me know that, yeah. No. Okay, let us hurry up here. Okay, functional groups in organic chemistry. If one of the more common functional groups is what we call the hydroxy group. The hydroxy group is essentially just an oxygen attached to hydrogen. Now what this is saying here is that this oxygen is attached to something. Okay? That is the hydroxy group. This here is what we call the carbonyl group. I know in your book sort of mixes the functional group and the classes of compounds. Okay? Sometimes when your book says what class of compound, what functional group is this, they are actually referring to class of compounds, but we're going to get to that shortly. Okay, the carbon-oxygen double bond is referred to as a carbonyl group. Okay? The carbon-oxygen double bond, also bonded to an hydroxy group, is referred to as a carboxy group. Then we have oxygen attached to an alkyl group, and that oxygen will be attached to something in the air. This group here is referred to as alkoxy group. When you have the nitrogen attached to something else and also attached to either hydrogen or carbon here, we call this amino. Those are some of the more important functional groups that we are going to be dealing with in organic chemistry. Now let us take a look finally, before we go, at the different classes of organic compounds. Different classes or families, sometimes we refer to them as families of organic compounds. Okay, by the way, if you see me use this R here, the R group, what this R group simply means is there is a carbon fragment somewhere. It could be an alkyl group, okay? Some carbon fragment somewhere. So from now on, you will begin to see me use an R. Okay. So therefore, supposing we have this here, this type of molecule in which you have a carboxy group attached to a carbon atom in the R group here, we call this class of compound carboxylic acid. You have this type of compound in which you have the carbonyl attached to two carbon atoms. This R will be carbon atom somewhere here. This is called a ketone. When you have the carbonyl group attached to a carbon atom and then an hydrogen atom, you call this an aldehyde. So these classes of compounds, you need to know them. There is no way around them. You need to know them. If you have this here, in which you have the carbonyl attached to an alkoxy, say attached to, let us say, methyl group or ethyl group, this could be any alkoxy group. This could be ethyl butyl group. We call this ester. You need to know all of these different classes of compounds. If we have two alkoxy groups, in this case, two oxygen attached to two carbon atoms, okay, We call this an ether. That class of compound refers.
Just put a R on the ester.
Yes, you could put yes, you could put R there. Very good. Instead of methyl, so it doesn't look like a specific ester, you could simply have R here, and sometimes to show you that this R could be different from this R, I could say R prime. Okay, that's an ester. Now you have an ether in which you have two carbon atoms joined to oxygen. An example will be this here. We call that dimethyl ether. Okay? Somebody is moving around. Huh? Okay. If we have this, okay, in which you have a carbon nitrogen triple bond, we call it a nitride. Now, if you take a look at your book, all of these different classes of compounds are stated there. You need to know them, okay? All of them, all of the different classes of compounds that you need. Yes? Yes, yes. You need to know those. There are not that many, okay, but I have given you most of them. Okay, but I do want to remind you, on Thursday, we are going to have a short quiz, a 10-minute quiz, on today's lecture, on Thursday. Once again, let me repeat, on Thursday, there will be a short 10-minute quiz on today's lecture, yes. Yes. No. Yes. Yeah, they're in the book. Okay, so let me give you back your quizzes. Yes. Why not?
You have to know this one.